Along with my colleague Nick Dominicovic, worked on the command and data handling subsystem, and I'll be presenting that for us today. Next slide, please. So the requirements of the CDH subsystem were to collect all instruments and housekeeping data up to 4 gigabits worth. This was to store the 3.1 gigabits or so data we're getting from the instruments during the science phase, and up to about 3 months of housekeeping data. The second requirement was to execute all the commands autonomously based on the elapsed mission time. This is due to the 6-hour or so round-trip delay out at Uranus for communications. And we're going to code our telemetry in a CCSDS file format. And our processor is capable of handling up to about 240 million instructions per second at 133 megahertz. But we only ever go at our maximum clock speed of around 59.7 megahertz, so we'll be clocking the processors to 66 megahertz. Next slide, please. For our analysis for the CDH subsystem, we researched modern interplanetary missions such as New Horizons, Messenger, and Mars Express. And we decided to go with an integrated electronics module as opposed to a separate box method. And we based a lot of our things on JPL's X2000 CDH architecture. And we're going to use a variety of computer assembly slices to accomplish processing, voltage conversion, data storage, tracking, telemetry and command, communications interface, and instrument interface. Next slide, please. Our main processor is a RAD750-3U from Bay Systems. This has extensive heritage on the New Horizons and MSL spacecraft. And we're going to semi-customize it with a mil standard 1553 bus controller to talk to the probe IM in order to send commands to it, along with the diviner instrument and the second redundant command and data handling box. It'll also be linked through the mil standard 1553 to the ASRG control units and the 3 PDUs on the orbiter spacecraft. Next slide, please. The second computer is our flight computer for ADCS and GNC, and it will also be a RAD750-3U from Bay. And it will be connected to all 5 reaction wheels and the 2 IMUs. Next slide, please. Our communications card, we're going to go with an X2000 system interface assembly. This is built to talk to the small deep space transponders. And it's going to encode our data for transmission to the deep space network. It's going to have 4 RS-422 full duplex transmit channels, and it'll also have the mil standard 1553 to talk to the small deep transponders as well as the tweeters. Next slide. Our instrument interface card is going to be a 256 micro D pin connector, which will allow for 20 full duplex LVDS or RS-422 connections. There's going to be 2 of these on the orbiter for redundancy, and it will be able to accommodate up to 12 sun sensors per flight with 3 excitations. And our star trackers will also be connected to the instrument interface card through the RS-422 channels that we have available.
So you have these I'll call circuit cards. You have them. There's a primary and a redundant.
Yes, there's 2 fully separate boxes.
Oh, it's just fully separate boxes.
And each of the boxes is connected to everything on the spacecraft through redundant lines.
Okay.
So if there's a failure in one, the other one.
We also have 2 of these components in each box as well. So the redundant of the wires are connected to the other slide.
Oh, so the redundancy is within the box?
Within each box and fully separated in the other box as well.
Okay. And then did I hear you say that it's coming out for one card, is the primary redundant coming out one connector? Or one large connector, or is it 2 different connectors?
What was the question? Sorry?
Your primary redundant cards, let's say they're speaking on out loud interface. You got a primary board and a secondary board.
Correct.
The connector coming out, is it all through one connector, or is it 2 separate?
It's 2 separate 128-pin connectors on each box.
I should have looked to the left. Thank you.
Alright, next slide.
And you have RS-422 interfaces to those instruments because they're old?
From the spec sheets that we got, some needed LVDS and RS-422, some needed just RS-422. And so since those are the instruments provided, we just set the data lines to connect to them. So the other IAM components is a secret non-volatile memory of 8 gigabits with 2 separate 4 gigabit rated drive, or separate rated flash memories. Each of them is going to be separately power controlled, and we're going to write all the data to both of them at the same time. There's going to be one of these in each of the IAM boxes. We're either going to have a DC-DC power converter to convert the 28 volt bus voltage to the 3.3 or 5 volts needed by each card. We assume that to be 74% efficient. And finally, for our analog sensor, we're using a trio assembly card made up of 6 trio chips, with each chip having 16 analog signal inputs. So that'll give us 96 telemetry channels per card. We're going to be using 3 of these on the orbiter, 2 on UPS, and 1 on the probe. And our total number of analog channels necessary was about 250, so we have some redundant channels also.
So the IEM is the integrated electronics
module. Yep.
And then that's got your computers in there?
Yep. It has all the cards that I've just gone over.
And is there, the memory is...
8 gigabit.
Okay.
And it's 2 separately rated 4 gigabit flash memory storage. We're going to write to both of them for redundancy.
Is it extensively reprogrammable in flight if necessary?
I believe it is.
Yes.
Yes. Next slide, please. So for redundancy on the 2 IAMs, the second IAM for both UPS and the orbiter will be off during the transmit phase of the ignition except for during critical burns, in which case it'll be running in a hot, normal power state. And it'll also be in a hot state for probe communications. And while just around Uranus, it'll be in a kind of sleep mode, so it'll be able to take over quickly, but for power reasons, we could not run it in a hot state around Uranus. Next slide.
So are there any concerns about single event effects that you take into account?
The RAD 753, I believe, has internal ability to account for bitlets.
So it's got error detection, correction?
Yeah, I believe it does. This is the same computer clone on you, correct?
So you're assuming that, right?
Yeah. No, we know from the spec sheet that it's able to account for them.
So what's it recover from? What kind of bit errors? Single bit errors, double bit errors?
I don't have the number off the top of my head, but I can get that to you afterwards.
Okay, so I think, so it sounds to me like, there's concern about it, but there's also other things you do, daily, weekly, whatever, to go through and check all your bits to make sure that the checks are right and correct. So you don't get double.
Yeah.
Has the radiation environment been specified to?
The radiation environment was specified to be 50 Krad, I assume, and all of our cards are rad hardened to 100 Krad. Next slide, please. You have a question?
Yeah, and unfortunately I had to step out, so to ask this already, or you told us stop. You've got 2 different processors. Is there any reason why you decided to use 2 processors as opposed to all in one?
We just decided why we chose an ADCM.
Well, we first decided that because we didn't really know how much processing each different types of subsystems. So we divided up because that's like a lot of other New Horizons divided up that way. So we followed that out. But once we learned here, we could all technically process it all in one, but then we could just keep 2 and have extra reliability as well. So I guess it's a trade, I believe. But
we did one processor where it failed, the other one could take up all of the.
So is that the way you've got the reliability center, or do you have redundant for each one?
We have a redundant within the box itself, and we have a fully redundant box. That makes sense.
So you've got 4 processor boxes?
There's 2 processor boxes, but each box has 2 processors within it.
Okay. And you've architected it so either box can pick up all the functions?
Yes.
yeah.
So you're...
Each box is connected fully through data lines to everything.
Yeah.
Okay.
Yeah.
Let me ask you a question. So you got this IEM, and you got 2 of them.
Mm-hmm.
One of them's going to be parallel.
Yeah.
So now I have 1 on. What happens if I get a DC-DC power converter failure? How going to switch, who's going to switch the backup power supply?
The PCDU?
PCDU can do that. If
Can
it
switch it.
detects that it's not getting telemetry data from the computer, it can switch over power to the other IEM.
And that IEM.
Where's the PCD? That's a separate box?
Yeah.
Other than this, that's not dependent upon the DC power converter?
Correct.
No, it's not. That's the DC power converter is just for the cards, for the command and data handling.
This is just to change the bus voltage to each other individual car. And it's 3.3 or 5
I'm
volts
thinking
instead of
we're talking
20.
here CD and H, maybe I'm confused. CD and H, the main computers are in this box. When one IEM is down, the other one's up. Like you said, they're eternally redundant.
Yes.
But then again, you know, I didn't hear anything about all A side or B side, but certainly the primary DC main power supply goes down. Who's going to turn the backup power supply on?
The power control distribution unit would turn the other IEM on, which is external, yes.
Thank you.
Yep. So the UPS system for the CDH is pretty much the same thing, but just scaled down version. There's no instruments on the UPS, so there's no instrumentation cards, and it has one less trio assembly card. It's a smaller spacecraft. It doesn't have as many analog channels needed. Next slide, please. And the probe IEM is actually an even more scaled down version of that, having just one computer, but still 2 boxes total, but only 1 computer per box, along with the communication interface card, analog telemetry card, and the DC-DC power converter. If there are no more questions. Yeah.
Yeah, I have just 2 comments, Brian. Think of this as the electrical equivalent of a mechanical system. Mechanically, we have really nice architecture layout of the bus and all the subsystems. I would expect to have seen a little block diagram showing the redundant channels, what they're all connected to, because you're connected to the power subsystem,
Yeah.
you're connected to the third floor.
We had one on our poster last night, if you were able to check that out at all. But we did not
I've never
really
seen an electrical block diagram of the entire satellite. Maybe
not the entire satellite, just the what's the
Yeah, no, I'm talking about the whole satellite,
Oh,
because
okay.
you're the heart of the you're the heart of the electrical system here. So that's one. The other comment I have is that in several places we saw the data budget. We talked about MIPS. That's spot on for the computer, but we also considered the size of the pipes, those data buses, how much headroom is in. 1553 is good to megabit per second, right? But you got 422, so I'd be interested to find out how much room you have in those data
We've
buses.
done the analysis, and we never get more than about 10% full on any bus.
That's an important piece of data because sometimes the data buses choke out and you got too much traffic going.
Yeah, but we never get over 10% full, correct?
Around there, yeah.
Around 10%. During
That would be
the
something to show in your data budget as
Okay.
well, as a line item, and how much room you have in your buses.
Okay. Now I'll hand it off to Sam Park.
So the primary box is in this system. How do you make
Huh?
How would you restate a summary of all the boxes? You don't have a functional block diagram, but what would you say are all the boxes in this system?
There's 2 IEMs. Our whole system is 2 IEMs per vehicle. And each IEM has the different cards that were gone through earlier. So like the probe has these 4 cards within each IEM. There's 2 IEMs total for the probe.
Okay, that provides your host unit.
That's the entire CDH system.
You have 2 parallel independent lines from the probe to the receiver.
2 independent what?
Relay links.
Yes. Right. Yes.
So the PDU is just provide the voltage over to the DC-DC power, right?
Yes, the PCDU distributes the power.
How is it sensing that you think that this DC-DC power to the primary would go off and fail, and your computers are off, your electrical power system just, what do you have in there that's going to sense that this box just went dead?
Well, the PDUs are also connected through a mil standard 5053 bus directly to the computer, so they're feeding back telemetry to each other. So it senses that nothing's coming out of the computer.
So I have a computer in my PDU?
Yes.
Yeah.
Oh, okay. I guess we'll get to that.
Power will talk about the PCDUs more.
Thank you.